So I was about to redo the solutions for Practice Exam A, and then I thought maybe you'd like to see how that goes. So I'm just going to go through the exam and show you how I do all the problems. It'll take me longer doing it this way than it would have otherwise, but I hope it's useful for you. So problem 1 says that the heavy box is initially at rest at the top of a ramp. Okay, so here's our ramp, and here's our heavy box. So it's initially at rest, and then a girl pushes the box down the ramp. At the bottom, she stops pushing, and the box comes to a stop due to friction. Okay, so she pushes the box all the way down the ramp, and the box is moving with some speed v, and it goes over here and comes to a stop. So v final is 0. For the entire process, the work done by the girl on the box was blank, and the work done by gravity on the box was blank. Okay, so if we look at my formula sheet here, work, the definition of work is the force dotted with the displacement. So this is the path. So this is the path that the box takes. It goes down, and then it goes horizontal. So that's the way it moves. So if we look at work equals F dot delta R, the sign is determined by this dot product between the force vector and the instantaneous displacement. So the box is always moving this way, and the girl is always pushing in the same direction. So her push force, so the force from the girl, is in the same direction as each delta R. So her force should be positive. So during this interval, when it's flat, gravity is doing no work because the force of gravity is down, and the displacement is in this direction. So that dot product is 0. But while the box is moving down the ramp, there's a component of that displacement, delta R, that's in the same direction as the gravitational force. Oops. So since this angle is less than 90 degrees, this will give us a positive dot product. So the answer is A. Okay, so how about problem 2? You suspend a weight from a 30 centimeter wire. The wire stretches by a centimeter. You cut the wire in thirds. You discard one piece of wire and suspend the same weight from 2 of the 10 centimeter pieces of wire. How much does each 10 centimeter piece of wire stretch? Okay, so whenever I see these problems where you're sort of comparing two scenarios, I figure out what formula applies. So in this case, this is a Young's modulus stress strain kind of thing. So we're going to be using this equation. So let's just write that down here. So force per area is the Young's modulus times delta L over L naught. Okay, so whenever I'm doing these kinds of problems, I write down the equation for each case. So over here for this case, let's say this is case 1 and this is case 2. So for case 1, F1 over A1 equals Y1 delta L1 over L naught 1. And for case 2, we have F2 over A2 equals Y2 delta L2 over L naught 2. Okay, so now I start looking to see if any of these variables are the same. Because this is true for this mass, and this is true for this mass. So let's see. So the force exerted on each of these scenarios is Well, over here it's mg because it's the force of gravity. It's going to be equal to the force of gravity that's acting on this mass. And it's going to be the same over here. So over here we have a choice. We can either say, okay, the cross-sectional area is bigger because there's two wires, or we can say that each wire is supporting half of this mass. So whichever you prefer, you can do. I think I'll go with the area. So that means that the force of gravity on this block is also mg. So these two forces are the same. So we'll say that F1 equals F2 equals F, which is just our applied force. So those are the same. So I can basically go in here and just get rid of these little subscripts because these two F's are the same. So how about area? Well, if this mass is hanging off of something with cross-sectional area A1, this mass has two of them. So the area that's relevant for mass 2 is actually twice the area of this one. So I know that these look really skinny, but in reality these wires are little cylinders and they have cross-sectional area A, and we're saying that this one has cross-sectional area A1. This one has two little cylinders, so it's got two like this. So the total cross-sectional area is A1 plus A1, which is equal to 2A1. And that's our A2. Okay, so now we know that A2 equals 2A1. So these are different. Now how about Y? So Y depends on the material. This was the same wire. We just cut it, so it's going to have the same Y. So Y1 is equal to Y2. And we can again get rid of these little subscripts. Good. Okay, so how about the delta L1? So delta L1 is something that we're given. So it says the wire stretches by 1 centimeter. So that means that delta L1 is 1 centimeter. Good, and we're looking for delta L2, so that's what we're after. So we don't know that yet. How about the original length? So the original length is 30 centimeters. And the original length of this is a third of that. So the original length for wire 2 is a third of that, which is 10 centimeters. Okay, so now we're ready. So let's just rewrite these and fill in everything that we know. So we knew that the F's were the same, but we don't know what F is yet, or maybe never. A1 is fine. Let's do everything in terms of the ones. So A1 is A1, and then we have Y. Delta L1 is 1 centimeter, and this is 30 centimeters. Okay, so over here to the next one. So F2 is just F. Now we need to write A2 in terms of A1. So A2 is 2A1, so we just plug that in here. That's Y, and delta L2 is what we're looking for, and we know that its original length was just 10 centimeters. Okay, so now we're after this, but we have F and Y in both equations, and A1. So what we can do is over here, we can move Y to the other side. So we'll have F over A1Y equals 1 centimeter over 30 centimeters. And over here, we're going to move Y over. So that's A1Y, and I'm going to move the 2 over to the other side. That's going to be 2 delta L2 over 10 centimeters. So now this is equal to this. So that means this is equal to this. And if you set those equal to each other, 1/30 equals 2 delta L2 over 10 centimeters, and you solve for L2, you'll get 1/6. So normally, if you're in really good practice with this kind of problem, you can do this much faster than I just did it. But you haven't seen a whole lot of these in your career, so I wanted to take my time and go through that one. Okay. So let's take a look at 3. The surface tension gamma of a liquid can be found by measuring the force F needed to lift up a circular platinum ring of radius r from the surface of the liquid. Ignoring gravity, circle all that apply. So the surface tension from the liquid tends to pull the ring back towards the surface. That's true, because as you lift the ring up, you're going to get little tension vectors that point down like this and want to keep the ring in place. The force required to lift the ring will increase if r increases. So they're saying if we take this ring and we make it bigger, will the tension force needed to lift increase? So the tension force here is gamma times L. And L is the length of the edge. So if this is the ring, and then you've got water, it's this distance the whole way around and on the inside in this case. It's those two lengths that determine the force. So if you make the ring bigger, you're increasing that little dashed line's length. So that's going to increase the force of tension. So this is also true. The force to pull the ring up will be the same for different liquids. So gamma is liquid dependent, so that's not going to be true. So let's get rid of that one. The force exerted on the ring by surface tension in this case is 2 pi r gamma. So 2 pi r is the circumference of the ring. But this ring has an inside and an outside. They almost have the same radius. Like this one has a radius r, and this one has a radius r plus a little bit. So they're basically the same. So if you add up those two circumferences, you're going to get 4 pi r. So E is also correct, but this one is not, because it didn't take into account that the ring is going to have sticky water collecting on both sides. So there's a little tension in here as well, and on this side too. Okay, so the next one says 2 identical spherical drops of water are falling through the air in free fall. Which of the following actions would decrease the total surface area of these 2 drops of water? Okay, so we know that more surface area takes more energy. So if you want to minimize energy, you need to minimize surface area. So we have 2 identical drops. So we could break the 2 drops into many smaller drops. So if you do that, you're going to increase the overall surface area. I like to think about a stick of butter, or a stick block of tofu or something. So if you take it and then you cut it in half, so you come in with your knife and you cut it in half and break it into 2 pieces, now you've just exposed new surface that wasn't exposed before. So the total surface area has to go up. So whenever you take something and you chop it into smaller bits, you're increasing the total surface area, which means you're increasing the energy. So this will do the opposite of what the question's asking for. Okay, so distort one of the drops into an elliptical, non-spherical shape. So spheres minimize or maximize the surface area to volume ratio. So it is the shape with the lowest surface area that you can get for that volume. So if you distort it, you're actually going to increase the surface area. So we don't want to do that. Decrease the surface tension of the water by adding a surfactant to both drops. So that would definitely decrease the energy because it's going to break up the little bonds that are on the surface and make them less sticky. So that one's good. Combine the two drops into a single larger spherical drop. That is good because it's the opposite of A. Combine the two drops to form a long, thin tube of water 1 meter long. Also not good because we know that the spheres are going to minimize the surface area for that volume. Okay, moving right along. This is a very good problem. So we have three situations where we have the same rod, the same stick in each case, and the stick is being held up by strings at 3 different angles. So the first thing we're asked to do is rank the magnitude of the force on the rod from the cord. Okay, so let's actually start by thinking about what must be true if these 3 sticks are in static equilibrium. So if they're all in static equilibrium, then that means that the sum of the torque has to be 0, the sum of the force in the x direction has to be 0, and the sum of the force in the y direction has to be 0. So let's start by thinking about the torque. And the hinge is the natural pivot. So let's start by placing our pivot at the hinge and see what information we get. So if we place the pivot at the hinge, we would calculate the torque by first drawing all the forces. So each of these sticks has mass. So there's going to be a gravitational force that's the same, because it's the same stick, in all 3 cases, pointing straight down. And then there's tension acting on the end of the stick. So this is tension for case 1, this is the tension for case 2, and this is the tension for case 3. So if we start by thinking about the torque, in each of these cases, the net torque is 0, so 0 equals, so this is half the length of the rod is the distance, so we would have L over 2, and this is a negative torque, times mg, and then we have to add the torque exerted by the tension force. And in all 3 cases, that would be the perpendicular component of the tension times the distance, which is L. Okay, so that means we can cancel these 2 L's, and we get that the perpendicular component of the tension is mg over 2. So this is saying that in each of these cases, the perpendicular component of the tension is the same. So that means the y component in each of these pictures is the same. So the y component of T1 is going to be equal to mg over 2. The y component of T2, which is the whole thing, is mg over 2. And the y component of T3 is mg over 2. So if we look at the y components are all the same. So if the y components are all the same, and these two also have x components to their tensions, then these two tensions must be bigger in magnitude than this tension. These two angles are the same, so the x components of T1 and T3 are opposite, but they have equal magnitude. So that means that these two are bigger and equal than this one. So T1 is equal to T2. These are magnitudes. And they're both bigger, equal to T3, and they're both bigger than T2. So one way to think about this is to imagine, instead of having a string here, pretend it was your arm trying to hold this stick up. Which of these cases would it be easiest for you to hold the stick up? Would you want to reach your arm out to hold the stick up, like you stand with your body over here and your little arm is stretching over here to hold the stick? Or do you want to hang your arm straight down to pick it up? You want this. If you're carrying a bucket of water, you hang it straight down. You don't hold it way out to the side because that would be a lot harder. That means you have to have a lot more force on the bucket because you've got less pulling straight up to counteract the force pulling down. Okay, so if that's true, now we want to rank the vertical force on the rod from the hinge. Okay, so we figured out that the vertical component of all three tensions is the same. And they all have the same FGs. So if we sum the forces in the y direction, and they have to equal 0, and we have the same perpendicular tension in each case, and we're subtracting off the same gravitational force in each case, then the hinge force in the y direction also has to be the same for each case. So these are all equal. Now how about the horizontal force on the rod from the hinge? Well, in this case, take case 2. So in case 2, I can redraw it. Here's our stick. We have gravitational force pointing down. We have a tension force over here. And we don't know what the hinge force is, so let's just give it a y component and an x component, and we'll solve. There's the x component. So if we sum the forces in the x direction, the only one that we have is the force of the hinge in the x direction. So that force has to be 0. Otherwise the stick would be accelerating. So this vector force can't exist, or this whole thing would accelerate to the right. So the hinge force, the horizontal hinge force for case 2 is 0. In case 1, part of the tension is acting in the negative x direction, which means that the hinge has to balance that by exerting a force in the positive x direction. Here, T3 is pulling the stick out from the wall, so the wall, or the hinge, must be exerting a force in this direction to balance that. So here, again, the force from the hinge, the horizontal force from the hinge, how should I say this? F, this is the hinge force in the x direction, there we go, for case 1 is equal to the hinge in the x direction from case 3, and those are both bigger than the horizontal force in the x direction from case 2 because that one is 0. Okay, so it's a good problem. All right, now for mass of a spring. So you place an unknown mass on a frictionless horizontal surface, you attach it to a wall, and the spring constant is 200 newtons per meter. When the spring is relaxed at its equilibrium length, the mass is at x equals 0. You stretch the spring. Okay, so we pull the mass out, release it, and record the position of the mass as a function of time as shown below. So we have position versus time. All right, so we have position versus time here. So if we look at this graph, I like to tell myself a story about the graph. So this is telling us the position. So this is saying we're starting over at, I don't know, x equals, this is about 3 centimeters. So we pull it out to 3 centimeters and we let go. So the mass comes back towards the equilibrium point, goes through it, squishes all the way over here. Then the spring pushes it back out, and it's off. So what's the period t? So the period t is the time to complete one cycle. So if we look at this periodic graph, we can find a peak and we can go to the next peak, and the time between those 2 points is the period t. So from this graph, that looks to be 0.4 seconds. All right, so what's the angular frequency, omega? So omega is related to the period. So omega is 2 pi times the frequency in hertz. And the frequency is 1 over the period. So this should be 2 pi over t. So if we do 2 pi divided by 0.4 seconds, that will give us 20 divided by 4 is 5 pi radians per second. Okay, so what is the maximum speed of the mass during the oscillation? So that's going to occur when it goes through the equilibrium position. And we showed that the maximum speed is equal to the amplitude times the angular frequency, which gives you the appropriate units of meters per second. So our amplitude, looking at the graph here, the amplitude is the displacement at the peak. So that's 3 centimeters. So our amplitude is 0.03 meters, and then we're going to multiply by our 5 pi radians per second, which will give us 0.15 pi meters per second. Okay, let's see what's next. Write an expression for the position of the oscillator as a function of time. Okay, so the first thing to figure out is this a sine or a cosine? So it starts at a maximum, so it must be a cosine. So our equation has to look like x of t equals the amplitude times the cosine of omega t. So in our case, our amplitude was 3 centimeters, and our omega was 0.15 pi radians, meters per second, times t. Okay, for which values of x is the magnitude of the mass's acceleration greatest? Well, we know that the net force on an object is directly proportional to that object's acceleration. So we should have the maximum acceleration where we have the maximum force, which is where the displacement is maximum. So if we look at this, it's maximum here, 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 and here, and here. So that's every maximum amplitude. So for which values of x is the magnitude of the mass's acceleration greatest? It's at x equals 3 centimeters, and also at x equals minus 3 centimeters, which occurs at every 0.2 seconds. Okay, what is the total mechanical energy of the mass in units of joules at these locations? Okay, so at the maximum displacement, all the energy is potential energy. So the potential energy max is 1/2 k a squared, because a is the maximum that x can ever be. So if we plug in numbers for that, we get 0.09 joules. And just to be clear, this was 1/2 k was 200 newtons per meter, and a was 0.03 meters squared. Okay, what is the change in the spring's potential energy in units of joules as the mass goes from x equals 3, so this amount, to xf equals 1? So that delta U is going to be U final minus U initial. So the final energy is 1/2, the final potential energy is 1/2 k x final squared. And we have to subtract 1/2 k x initial squared. So that gives us, we could pull out this 1/2, I guess, and the k. So we'd have x final squared was 0.03 centimeters squared minus 0.01. Oops, this is just in meters. I already converted, silly me. Meters squared. And if you do that math, oops, I switched my final and my initial. This was my initial. So this should really be a plus and this should be a negative. I'm sorry about that. I just put the wrong x. This one, x final, is actually that value, and this is that value. So you'll get 0.08 joules. Okay, so now for this nice torque problem. So here we have a uniform plank, mass m and length L, suspended from the ceiling by a pair of ropes. And then we have a little mass m on the plank, a distance x from the end. We want the minimum value of x for which the plank will not tip. Okay, so the first thing is we want to figure out what does it mean for the plank to tip, because that's going to give us our constraint. This is kind of like those problems where we say, when will this thing lose contact with the surface? And it's when the normal force goes to 0. So we're going to have something like that. So if we look at this situation, if this little mass moves over here, it's going to weigh down this end, and then the whole plank is going to pivot around this point, and this end will lift up. And that means the tension in this string, if this string is slack, it has no tension. So the tension in this string, let's call it string 2, is going to go to 0 if this thing tips. Let's call this tension T1. Okay, so we need to take T2 to 0. So let's finish drawing a free body diagram for this. So we need the weight. The weight of the plank is going to act in the center, right there. We have T1, we have T2, and we're going to have the weight from Marvin. FG Marvin is going to be, Marvin's mass is little m, g, and this is big. So this is FG plank. Okay, so this threshold is met when T2 goes to 0. So this is the physical pivot. So I'm going to use the condition of static equilibrium, because we want the very second, where basically this whole thing is just balanced around this point so that T2 is not carrying any weight. So let's pick this as our pivot. So we want the sum of the torque around this pivot to be 0. So 0 is going to be, so now let's start with Marvin. So Marvin is this distance, which is 1/3 L minus x. 1/3 L minus x. And this is a counterclockwise torque, so it's positive. So we have 1/3 L minus x times Marvin's weight, which is mg. Now the center of mass of the plank, we have to figure out what that distance is. So this distance is L over 2, and this distance is 2/3 L. So that means this distance right here is 2/3 L minus L over 2. So let's see what's that. That's 4/6 L minus 3/6 L, which is 1/6 L. So this little distance right here is 1/6 L. This is a clockwise torque, so it'll be negative. So we'll do a 1/6 L, and then we're going to multiply by the weight. So that weight is mg. And then we have this last force over here, but it's gone to 0. So if the force is 0, then there's no torque. Okay, so now we need to solve for x. So we'll move this to the other side and distribute this through. So we have a 1/6 LMG is 1/3 LMG minus mgx. All right, so I'll flip these two. And so the g's cancel. So x is, if I divide both sides by m, we have 1/3 L minus 1/6 L m over little m. And just for fun, oh no, you can't see that. You got that? Okay, just for fun, I'm going to factor out 1/3 L. So this will be 1 minus 1/2 m over m. Okay, so is there anything about this we could check? Like, if this is just gonna balance around this point, then we only have these two forces. So if Marvin's mass is equal to the Planck's mass, this distance should be the same as this distance. This distance was a 1/6 L. So if we set the two masses equal to each other, this distance should also be 1/6 L. Let's see if that's what we get. So if m equals little m, then we know that x should equal 1/6 L. So let's try plugging that in. So if these two m's are equal, they will cancel out and become 1. So we get 1/3 L times 1 minus 1/2, which is 1/3 L times 1/2, which is 1/6 L. So that's one check you could do to make sure that this is the right expression. Okay. Let's see. Okay, so if then Marvin sits a distance L over 3, x equals L over 3, right where the left cable is attached, what are the tensions in each of the two cables? So if we just redraw this, so you didn't have to solve the first part to get this part. So this is our T2, and our T1 is over here at, this is a distance 2/3 L. This is a distance 1/3 L. And we put Marvin right here. Alright, so his weight is pulling down this little mg, and the center of the plank is here, and that's big mg. So let's first solve for T2. So I don't know what T1 is, and I don't know what T2 is. So if I'm going to solve for T2, maybe I'll put my pivot at T1. So then T1 doesn't show up in my equation, and let's see if it's solvable. So if we sum the torque around our pivot, we need this. This is a negative torque. We're at 1/6 L at that point, and we have a mass times g. And then we need a positive torque a distance L away times T2. And this has to be 0 because we're in equilibrium. So if we solve for T2, let's get rid of these L's. So that means that T2 is 1/6 mg. Oh, this was not L. This was not L. Okay, so what did I do? I was supposed to use the distance from the pivot, so I did that correctly for the first term. But I did not do it correctly from the second term, because I need to go from the pivot over to the point where the force is applied, which is actually just a distance of 2/3 L. So instead of having an L here, I should have had a little 2/3. So this is not correct. This should be 2/3 L. So we have minus 1/6 mg plus 2/3 T2 equals 0. Now, 2/3 T2 is 1/6 mg. And now if I solve for T2, I am going to get 1/4 mg. Because this will cancel with this and put a 2 down there, so I'll get a quarter. So 1/4 mg. Good thing I caught that mistake, huh? Physics is hard. Okay. Ooh, a merry-go-round. Alright, so a child sits on a merry-go-round initially at rest. So initially at rest, that means that this is the thing that's going around, so there's probably going to be an omega, and it also means that, so it means that omega and v are both 0. So starting at t equals 0, the merry-go-round is given a constant angular acceleration, which increases its angular speed for 8 seconds. The child is seated a distance 2.5 meters from the center. Calculate the magnitude of the final angular velocity of the child at t equals 8 seconds. Okay, so we have our initial omega. You want angular velocity, so let's think in terms of angular velocity. So our initial angular velocity is 0, and we know the angular acceleration. And we know a delta t. And we want omega final. So we need to use a kinematic equation for the angular velocity. So we're going to use this one. Final, if we have constant angular acceleration, we can use the kinematic equations. So the final angular velocity is the initial plus alpha t. So for us, this is 0. So alpha is 0.06 radians per second squared. And we're going to multiply that by our t, which was 8 seconds. So we'll get 0.48 radians per second. All right, calculate the magnitude of the final tangential velocity. So the tangential velocity is related to omega by an r. So the tangent is just the radius where the kid is sitting times the omega final that we just calculated. So that's 2.5 meters times 0.48 radians per second, which gives us 1.2 meters per second. All right, so how about the total distance traveled by the child? Well, we have all these angular quantities, so let's calculate. If we want the total distance, we could also figure out how many radians we went through and then convert those radians to a distance traveled around the outside length. So our change in the angle is, by the kinematic equation, our initial angle we wrapped into delta theta, and then traditionally this would be the initial speed times t plus 1/2 alpha t squared, just the kinematic equation for position in the radial coordinates, in the radial variables. So this was 0, so we don't have to worry about that. So this is 1/2 alpha t squared. Okay, but this is going to give us a change in angle, and we want to convert that angle to distance. So if we move through an angle theta, and this has radius r, this distance that you've traveled is called s, and s is equal to r times theta. So to get the distance, delta s, we just need to take the radius and multiply it by our displacement in angle. So that's 2.5 times this 1/2 at squared. 1/2 alpha was 0.06 radians per second squared, and then we did 8 seconds squared. And that gives us 4.8 meters. Okay, so if the mass of the merry-go-round itself is negligible compared to the mass of the child, how much work is done on the system between t equals 0 and t equals 8 seconds? Okay, so we're asking about work. So there are a few things we know about work. We know that the work done by some force is that force dotted with the displacement. We also know that the net work done on an object is equal to the change in that object's kinetic energy. So this one looks promising. This one seems promising to me. So the only thing that's doing work on this system is whatever is causing the angular acceleration. And that's what we're asked for. So if we want to calculate the net work, all we have to do is calculate the change in kinetic energy. So the final kinetic energy minus the initial kinetic energy, well, this was 0 because it started at rest. And this thing is rotating, so it's going to have rotational kinetic energy, which is 1/2 I omega squared. So this, since the merry-go-round doesn't have mass, we don't need to include that as a disk or anything. So we only need the moment of inertia of the child. And that moment of inertia is the mass of the child. We'll treat the kid as a point mass, is m times the radius the kid's sitting at squared, and then we just have to multiply it by omega squared. So we found omega earlier, we know r, we know m, and if we plug all of that in, we get 21.6 joules. Okay, last but not least, we have Tim, and he's snowboarding, and there's a strong horizontal wind blowing on him. And his snowboard is frictionless. There's no friction between him and the slope. And we want to solve the below, and we're not allowed to use Newton's laws of motion. So, to figure out the work done by the wind on Tim, let me just slide some paper under here. So we know that the work done by a force is the force dotted with the displacement. So for Tim here, the wind is in this direction, and his displacement is in this direction. So we need to figure out what these two vectors are, and we need to dot them. So how should we do that? Well, there are a bunch of ways to do it. One way is to find each vector and then take the dot product of those two vectors, component-wise. So let's do it that way. So if we give ourselves some regular components, or regular axes, we can write these two vectors in components using those axes. So the force of the wind is totally in the positive x direction. So we would get F wind, and there's no component in the y direction. So what's our delta R? Well, what do we know about this triangle? So we know that this angle is 10 degrees. And we know that he travels to an elevation 100 meters below where he began. So that means that this distance here is 100 meters. So what's this distance? Well, we know this angle and we know this height, so that's going to fix this distance. If we took the tan of this angle, we said tan theta would be the opposite, 100 meters, over the adjacent, which is this distance that we're looking for. Let's call that delta x. Then delta x would be 100 meters over the tangent of 10 degrees. So for our r, the distance in the x direction is 100 meters over the tangent of theta, but we just have to be careful to put a negative sign on that, because final minus initial is going to give us a negative displacement in the x direction. And then in the y direction, he travels minus 100 meters. Okay, so now if we do the dot product of these two vectors, we need to multiply the x components together and add that to the product of the y components. So the work done by friction, the work done by the wind is F wind dotted with delta R, which is F wind times negative 100 meters over the tangent of theta, and then we would add 0 times minus 100 meters, but that is 0, so we just get force of the wind is negative times 100 meters over the tangent of 10 degrees. And we're told that the force of the wind is 50 newtons. So if we plug in 50 newtons here, we're going to get about 28,000 joules. Okay, so you could certainly do that another way where you find the angle between the two vectors instead of doing it component-wise. Find the angle and just use the fact that this is the magnitude of the wind times delta R times the cosine of the angle between them. You just have to make sure that you know the correct angle between them. Either way is totally fine. It's whatever you prefer. Okay, so what else do we need to find out about Tim? Well, we want to know the work done by gravity on Tim. So the work done by gravity on Tim is here's delta R, and the work done by gravity is down. And by now you've probably seen that no matter what path you take, it's only the change in the height that matters for the work done by gravity. So this is going to be positive mgh because the motion is in the same direction as gravity. Well, not in the same direction, but this angle is less than 90. So that's all. So you just plug in the 100 kilograms, the g, and the 100 meters, and you're going to get 98,000 joules. So what is Tim's speed after having traveled to this lower elevation? Okay, so now we want to know his speed, and we're not allowed to use Newton's laws. So we need to find speed. We're probably going to need to use the work kinetic energy theorem, because this has a V in it. So if we know the net work done by all the forces, we can figure out the change in kinetic energy. So what's the net work done? Well, the net work done in this case is the work done by all the forces that do work. So if we look at Tim, he's got gravity pulling down, he's got the wind in his face, and he's got a normal force. But the normal force isn't going to do any work. So the total work is going to be the work done by the wind plus the work done by gravity. And that's going to equal his change in kinetic energy, which is 1/2 mv final squared minus 1/2 mv initial squared. Okay, so his initial speed was 0, so his initial kinetic energy was also 0. So we could then just solve for VF. VF is going to be 2 over m times the work done by the wind plus the work done by gravity. And we have to take the square root of that. And we already calculated these two works. So the work done by the wind was, whoops, we forgot. So over here in part A, we forgot something. So there was a little negative sign here, but I didn't draw it over there. And that's important. And we know that the work is doing negative energy because it's going to slow, or the work is doing, the wind is doing negative work because it's going to slow him down. The force is in the opposite direction to the delta R, so the cosine of the angle there should be negative. So the work done by the wind is minus 28,000 joules, and the work done by gravity was a positive 98,000 joules. And if we calculate a number for that, we're going to get that VF is approximately equal to 37 meters per second, which seems a little bit fast for a snowboard. But I don't snowboard. And that's it.